So what about kratom and mitragynine? So we're going to focus a little bit on mitragynine because it's received the most attention. One, it's the most abundant alkaloid in the plant, so it's the most easily extracted, isolated, purified, and then studied. We know that very few deaths are attributable to a kratom product alone, and even those that are attributed to kratom alone, there could be extreme circumstances. One, in terms of overdosing or very high doses, and I'll talk about that at the very end of the talk, or it could be adulterated with unknown synthetic compounds. We've also reported some adulteration of kratom with oxycodone and morphine that's been available in the marketplace. And why someone would spend the money to go through and put a more expensive opiate into a product that's very inexpensive is something just seeming to me to be nefarious and sinister. But it happens. Mitragynine, we know, is a partial mu opioid agonist. It causes about 40% maximal effect in G protein activation. And the excitement about it was that it's also a biased agonist. In other words, it signals only through the G protein mechanism and it doesn't recruit beta-arrestin. Why is that important? Well, a lot of molecules are under investigation and development as opioids with low respiratory, depressive, and constipative effects because it's believed that not recruiting beta-arrestin actually pushes away some of the liabilities and side effects. And so a lot of that work first came out from Andrew Krugel and Davor Sem's lab at Columbia. They've been working hard on this, as well as Shrishta Majumdar, who's also funded in this area, in the chemistry area, and really been producing some great material that we tend to go back and forth in the literature on, and it's been fun. What about the therapeutic potential, though? We've looked at it primarily from the source of an opioid detoxification. So really having the potential to place several medications. I mentioned that it has opiate activity, but I'm going to show you that it's much more disruptive than just opioid activity. In fact, I think it's really something that is causing a lot of problems on how to deal with this on many levels because of the really disruptive pharmacology that it's causing. It has adrenergic, serotonergic activities as well as others. But if you could combine all of those into one product, you might be able to improve medication adherence and completion of detoxification. We also have looked at it with NIDA as a potential medication-assisted therapy. It is used informally to reduce opioid use, and kratom withdrawal is mild. Really, on the subjective opioid withdrawal scale, it's in the upper end of mild, but it's not in moderate, and it's certainly not in severe. And as we said before, polydrug users report kratom also may reduce methamphetamine use. But the biggest problem, and one of the things that we're excited to be able to start exploring, is having a standardized product to really get into clinical trials and evaluate any of these therapeutic potentials. There are other therapeutic potentials, I think, that can come out of this in terms of novel analgesia measures, as well as potential antidepressants and mood elevating elements. And I'll dissect a little bit of that as we go. One of the great things about the University of Florida is that we have our agricultural school and our health sciences all based in the Gainesville campus, which is one of only 3 universities in the country that has that ability. And so I've really been fortunate to form a great collaborative relationship with Brian Pearson here, who is located in our Apopka campus, which is just outside of Orlando. And these are kratom trees that we're growing in that center. We have about 100 trees in ground, and we have hundreds, close to 1,000 trees in greenhouse, which, if you can see my picture what I'm speaking at, that's actually one of the greenhouses that we have full of trees. Interestingly enough, we had to wait until we had enough biomass to really analyze these trees. And what we've learned is that we have 3 existing chemotypes. So not different, again, from cannabis, where we have a high mitragynine producing chemotype, and we have a chemotype that produces almost no mitragynine, and then we have something that seems to be in between. We're working with Sarah O'Connor at the Max Planck Institute to look at the biosynthetic pathways within this plant. We're also working with plant geneticists here at the University of Florida to really start to understand what the differences are, and doing deep dive DNA barcoding to really see how closely related these different chemotypes are. But anyway, that being said, it's because of the interest in trying to get a homegrown species so that we might be able to develop a product that's more similar to the traditional use for study in the United States than having to rely on these dried leaf materials, which, by the way, undergo post-harvest oxidation. And so you can imagine, just thinking about a dried leaf versus a fresh leaf, you've got oxidative chemistries that have taken place, and then many times have changed the composition of the alkaloidal content. And we'll talk a little bit about that as well.